This is Solve It for Kids.
Hello, my amazing and curious friends. My name is Jennifer, the Dean of all things STEM and STEAM, and this is Solve It for Kids, the podcast that gives kids and families a peek inside the real world of scientists, engineers, and experts as they solve problems in their jobs using creativity, cooperation, and critical thinking. And now please welcome to the show my podcast partner, Galactic Space Geek, Jeff Gagne.
Hello, Jennifer, and hello, listeners. Today is going to be awesome because I love episodes when we are answering a question that I didn't even know to ask.
Oh, exactly. So what problem are we solving today?
What would happen if we didn't have magnets?
What would happen if we didn't have magnets? I'm guessing this is something pretty big. Who is our guest today, Jeff, that's going to explain all this to us?
Our guest today is the expert on the topic, Dr. Dario Arena, and he is Associate Professor of none other than Physics at the University of South Florida.
Welcome to the show, Dr. Dario.
Hello. Thank you so much for having me here. Very happy to be on Solve It for Kids.
Well, we are excited to have you. We're going to talk about all things magnetic, which is going to be a really cool episode, I think. So I have to ask, were you that kid that played with magnets?
Yes, I was the kid who played with magnets.
Yes.
And I wanted one of those giant magnets that the Roadrunner had, that the
Oh my
Coyote
gosh,
had, that he used to
yes.
catch the Roadrunner with. I really wanted one of those.
Oh, yeah. Those, I think we all did as kids, yes.
Oh, yeah,
I like
exactly.
that. So I do need to ask now, what was the biggest or strongest magnet you had when you were a child?
Yeah.
When I was a kid, the magnets were, I'm old enough to be sort of an earlier generation of magnets where they had that U shape, and those were not that strong.
No,
So
weren't.
now we have much better magnets that are shaped like a bar.
Right.
And those are much, much stronger magnets. And you can do all sorts of fun things with them. You can even levitate trains with those kinds of magnets.
Yes.
Whoa.
That's very cool. So
Yeah.
how did your love of magnets as a kid turn into a career down the road?
Well, the love of magnets sort of led me to physics.
Okay.
Because I wanted to understand how magnets work.
Yeah.
And so to understand how magnets work, you have to understand some physics. And so that's kind of led me to the path of trying to figure out the things that I should study, which turned out to be physics. And then eventually when I finished my PhD, my doctorate, I got a job using X-rays to look at magnets.
Wow.
Yeah, so that was very cool. That was a really cool job. And then that led to my working on magnetic materials and sort of understanding how they're put together and their properties using this really cool instrument called a synchrotron.
Wow.
Yeah, so that was a lot of fun.
That sounds
We have
fun.
got some cool stuff to talk about.
Yeah.
So I want to start at the beginning. Can you describe for us in sort of basic terms how a magnet works?
Yeah.
So to talk about how a magnet works, I got to talk about a property called angular momentum. And that's a big word.
Okay.
But angular momentum is kind of like the mass of an object, but it's a little bit different. So the mass of an object is related to a property that we call inertia. Basically, how difficult is it to move that object?
Yep.
Angular momentum, we kind of think of, we use a term called spin, which is a little inexact, but you can kind of think of it that way. So an example of angular momentum is a bicycle.
Oh, yeah.
Okay.
And a bicycle, if you just are not pedaling and you try to sit on a bike, you'll tip over.
Yes.
Oh, yeah.
Yes. You can't
But if
sit on
you-
a bike if you're not moving.
Yeah.
Exactly. It doesn't work. You got to pedal. You got to have those wheels spinning. when the wheels spin, they produce a property called angular momentum. And that angular momentum keeps you balanced.
Oh.
So that is, and how
Wow.
magnets work is essentially pulling together all the angular momentum of the electrons in a material in a way that they stabilize the direction of those little tiny angular momenta of the individual magnets.
I
So
did
you
not
can-
know this.
I
This
have
is
never
very
heard it
cool.
explained this
No.
way.
Very,
Okay.
very cool. So it relies on this sort of really basic property of electrons called angular momentum, the way that many other properties rely on the mass of objects.
Okay. So how does this relate to what we know about magnets, how it attracts other magnetic objects or repels them? How does that angular momentum play into that?
So everything has angular momentum.
Okay.
The trick is you can kind of the trick or the problem, depending on how you want to look at it, is that most materials, all of that angular momentum cancels out. So think about a bicycle wheel. If a bicycle wheel is spinning in one direction, it's going to have angular momentum in one direction. If you have a second bicycle wheel that's spinning the opposite way, it's going to have an angular momentum as well, and they cancel out.
Okay, got it. Okay.
And in most materials that we experience every day, that's what happens to the angular momentum of the electrons. They just cancel out.
Okay.
But
All right.
there are some special materials that we call magnets,
Right.
where they don't entirely cancel out. So now I have more, let's use left and right.
Okay.
I have more angular momentum pointing, let's say, to the left than it does to the right. So now I've got a net angular momentum pointing to the left. And that angular momentum, if you study the math a little bit, produces a magnetic field that then can be used to attract objects.
No kidding. Okay.
I'm kind of blown away here. Wow.
Yeah, I really have
just
never
thought
heard
they're
it.
little magnets, That's so
Yes.
cool.
Yeah, they
stick
are
stuff
little
to the
magnets all the
fridge.
way down to the level of electrons.
Right. But I mean, I didn't really think about how the electrons move in the field that they create is how all of it works.
Yeah.
Okay.
So
I'm
that
impressed.
leads me. You were mentioning earlier that we now have bar-shaped magnets instead of those U's. And if you use one end of the bar, it will attract something. And if you use the other end of the bar, it may repulse something.
if that other object is magnetic, it's sort of intrinsically magnetic. So if you have one of these bar magnets, they have two sides to them. We typically call them north and south.
Right.
And if you sort of, most people use magnets to stick stuff on their fridge, right?
Right, exactly.
So, yeah.
My fridge is covered with magnets.
Exactly. Yeah, that's what we all do. We put pictures of our kids, our dogs, notes to remember to pick up the milk, all sorts of things. List of chores go up there too. But when you're using a magnet to stick something to a fridge, it doesn't matter which side you're using, north or south, because the material underneath the fridge, it has electrons that respond to the field that's produced by that north or south pole of the magnet. So it's going to produce an attractive force either way. However, if you bring a magnet, a north pole, let's say 2 bar magnets, and you put their north poles together, you're going to feel a force that is repulsive, that wants to push the 2 objects away. If you have a north pole next to a south pole, now you get an attractive force, and it wants to pull the 2 objects together. So opposites attract, right?
Yes.
So north and south will attract, north and north will repel, south and south will repel.
Okay. So you're saying that every material has types of magnetic qualities in it. It's just not necessarily magnetic as we would think about it. Is that correct?
Yeah, that is correct. And I told you a tiny, tiny lie.
Okay.
And I'm sorry about that. I said that most materials are not magnetic, and that is almost true. There's this property of all materials called diamagnetism, which is another big,
Ah.
giant word. But that is something that occurs when you stick an object in a really, really strong magnetic field. And then you can actually make that object very, very, very slightly magnetic. And you can do some cool things with that.
Oh.
So, for example, there are some videos on the web that you can find called the levitating frog,
Oh my
Okay.
gosh.
where you can actually put a little tiny frog in a droplet of water, and you put it in a big magnetic field, and the frog is happy because the water and the frog, because most of us are animals are mostly made up of water,
Right.
has this little diamagnetic contribution. And the diamagnetism is like that North Pole with the North Pole or the South Pole with the South Pole. It's a repulsive force.
Right.
So you can now get that little frog in its bubble of water to float in midair.
Oh my
And
gosh.
No
there are some
kidding.
videos online about this. There's a guy called
Wow.
Andrew Geim, Geim. And he was the guy who did this levitating frog experiment. I don't know, 20, 30 years ago, something like that. He's a
Okay.
really smart guy. He discovered later on, after he did the levitating frog, he discovered a material called graphene, which is a
Oh.
super, super cool material.
Yep. I know all about graphene. Yes.
Yeah, and he ended up winning the Nobel Prize. But
Oh,
he
yeah?
started out using big giant magnets to do all sorts of cool experiments, including levitating frogs.
Okay. Wow. That really does sound cool. And it's got to be a cool experiment if you are a guy that works with all of this stuff and you
Yeah.
think it's that cool.
It is super cool.
So we can't let Andrew steal any of your limelight. So for this episode, what kind of cool experiments, how do you work with magnets and magnetism?
Yeah.
So what I do now mostly is I study a type of magnet called a thin film magnet.
Okay.
So what does that
Okay.
mean? It means that basically I stack different magnetic materials together, or magnetic materials and materials that aren't magnetic, and I try to get some cool new properties out of those materials. So why do we do something like that? And I'm kind of like my dog. I'm always motivated by food.
I think you just pulled all of our listeners in.
Great. So the analogy I like to use is a peanut butter and jelly sandwich.
Okay.
So I like bread, I like peanut butter, I like jelly.
Yeah.
Excellent.
But if I take a slice of bread and I put a layer of peanut butter on top, and then I put a layer of jelly on top of the peanut butter, and then I put another piece of bread on top, I've got these layers in there.
Yes.
When I take a bite of that, it's much better. It has different properties than the individual bread or the individual peanut butter and the individual jelly. And it's that kind of stacking on top of one another that we do kind of at the atomic level in my lab. So growing new kinds of films and then checking out their interesting magnetic properties.
So to what end? Are you trying to create new materials that do cool things? Is that what you're looking for?
Yeah. So we are trying to create materials that we have a couple of different sort of projects going. We have materials that will vibrate back and forth. The term we use is oscillate at really, really high frequencies in a range of frequencies called terahertz, which is kind of in between radio and microwaves and visible light. It's kind of a hard part of what's called the electromagnetic spectrum. It's a hard region to operate in. So we're trying to develop materials for that. And we're also using these materials to do something called spin injection. Again, going back to that angular momentum that we were talking about, we want to inject that angular momentum into a material that's normally not magnetic. For example, graphene.
Oh, wow.
Okay.
So there are advantages of using the materials that I grow in my lab for this kind of new material development. And then that will allow us hopefully to get, faster electronics, new kinds of communications.
About to be my question on what types of applications for this stuff.
Yeah, so it has to do with getting electronics that work faster, electronics that also interact with light. So you can have optoelectronics for things like deep space communication. Really high frequency stuff. So it's things that, we might be talking to people on Mars one day using the kinds of technologies that the materials we're developing permit.
Wow.
And I assume that would be faster than the capability we have now, because of course it all depends on how far Mars is based on Earth. And, I've heard estimates anywhere from 45 minutes to a couple of hours potentially to talk. They believe to talk to astronauts when we get there.
Yeah, we can't change that. That's based on the speed of light, and we can sort of transmit information that will take us, however far Mars is at that particular instant.
Right.
What we can do, however, is we can squeeze a lot of information into the communications that we send.
Okay.
So it doesn't make the talking back and forth faster, but it allows more information to be sent in a short amount of time.
Gotcha.
That would also be helpful, though, right?
Sure.
Instead of sending one direction and then waiting to come back and then sending another step. And, if you could send 10 steps at one time or something.
Sure. Like if we wanted to send them the new Guardians of the Galaxy movie over to Mars, we're going to need to put in a lot of information.
Everybody needs that movie.
Yeah.
Yes.
Excellent. So I'd like to jump into your brain or your team's brain in your lab just a little bit on this. Sounds really, really cool. I have no idea how you come up with the ideas to test, to create these new things that you're creating. How does that happen? How do you think about oscillation over here or adding angular momentum over here? How does that process kind of work?
It's a little like learning a new language.
Oh.
Wow.
Right? So what happens is, if you're learning a new language, you learn with some basic vocabulary, right? So you learn what's the word for dog, what's the word for play, what's the word for rain.
Right.
Sure.
And then you start stringing those things together in sentences. And then you start stringing the sentences together in paragraphs. And then it gets, it can get more complicated and more complicated and more complicated. And as you're doing that, you're also reading in the new language. And so the way that we come up with ideas is by reading a bunch of other people's work and then thinking about how we do our experiments and that often sort of triggers new ideas for us.
Okay.
And the best part of it is when you're doing some kind of experiment and you get something that you don't expect.
Oh, okay.
Yes.
That's when really cool things happen.
Okay. So the question for the episode, because now we've explained a little bit what magnets are, is what would happen if we didn't have magnets or magnetic materials? So can you tell us what would happen?
It would be a complete catastrophe.
Oh my gosh.
Yeah, catastrophe.
Think about all the fun things that you do now. You get to maybe drive your car. You get to go to ride roller coasters. Right? You get to use your smartphones. You get to stream TV shows.
Yep.
Sure.
You get to use electricity.
Oh,
None of that
that's
would
true.
exist without magnetic materials.
Oh my gosh. Talk about something I haven't ever thought of.
Yeah.
We would be back to the Bronze Age without magnetic materials. And there's another problem. The Earth itself is a giant magnet.
Yes.
Yes.
And it produces a big magnetic field. And that magnetic field protects us from kind of radiation that the sun puts out.
Right.
Because the
Right.
sun spits out all sorts of things, including charged particles, electrons, protons, and what are called alpha particles, which are the nuclei of helium atoms.
Right.
That stuff would bombard the Earth and make life impossible if it wasn't for the protection of the Earth's magnetic field.
Right.
Wow.
So,
So
yeah,
magnets
so-
are a big deal, is what you're
They
saying.
are a
Yeah.
big deal.
Yeah. Turns out Earth without a magnetic field is Mars.
Pretty much, yeah.
Okay. So you said we would be back to the Bronze Age if that happened. Is magnetism and magnetic materials something that was discovered along the way of humanity being alive?
Yes, actually, some of the oldest, let's say, technological materials turn out to be magnets.
Ah.
So there's this really old material called lodestone,
Okay.
which is
I've heard
an
of it.
iron oxide. The chemical formula is Fe3O4, 3 iron atoms and 4 oxygen atoms.
Okay.
Lodestones there's information dating back to 1,000 years BCE, before the Christian era, of people in Mexico in what was called the Olmec civilization, using lodestones for ceremonial purposes. Those were also the earliest compasses, magnetic compasses, that people used to navigate around the world. There are written records going back to ancient Greece, to 600 BCE, and then the earliest compasses were in China in about 200 BCE.
Okay.
So magnetic materials have been around technologically for a really, really long time. And then, as we entered into the Industrial Revolution and slightly before that, we started getting better and better at understanding the magnetism and then using it for our purposes. And one of the biggest and most important uses is to generate electricity.
Yes.
Right.
Which we like.
we do kind of like that. Yes.
Yeah.
That's very helpful. So I'm curious. So if you were going to talk to a kid these days, in grade school, high school, whatever, and they want to go into this and kind of do what you do, what would you tell them? Where would they start?
Well, I'd say, go to your library. My go-to answer for most things for kids is go to your library and ask a librarian to help you learn a little bit more about it. And then in addition to that, a lot of universities and a lot of laboratories will run things like science summer camps.
Right.
And that is a great place to get information. There are some of the big laboratories, if you're lucky enough to live next to some of the big laboratories in the US or other parts of the world, sometimes, usually a few times a year, they'll have open houses. And then you can go and check those places out and look at the really cool experimental tools and toys that the scientists get to play around with.
That sounds fun.
Yeah. And then get involved if you're in high school or even in grade school, get involved with a STEM club, a makers club. All these things kind of get the same parts of the brain working that you would need to learn about magnetic materials.
Yeah. So I have to say that, so you also worked at Brookhaven Lab for 14 years. So I got to visit there, which was amazing. And then CERN had an open day that I got to go to back in 2019. And I got to see the Alice detector, which was just amazing.
I will bet.
It was amazing. Yeah.
I'm jealous. Yeah.
There's a book on particle physics forthcoming.
Awesome.
But yeah, it was, so any of those things are amazing. And there's really cool labs all over the place. Even at universities, they may not have big, huge particle detectors, but they have really amazing facilities. So yeah, I think that's a great place to check out.
Right. Yeah. I mean, when we were in Ireland, I crashed a STEM event at Trinity College in Dublin.
Nice.
Oh, how fun!
So we went to see the Book of Kells, and then we're walking around the university, and I see a sign for STEM, something like STEM Open Day. I'm like, well, I gotta go check this out.
Gotta go walk through there.
Yeah.
Gotta find out who's doing physics in there.
Exactly. Yes. So then I started grilling them about what they're doing and what their activities are. I'm like, I am going to steal that idea.
There you go.
Nice. So I want to back up before Jen gets us moving along. All the way to the beginning, there was something you said I wanted to go back to ask you a question about. What does a magnet look like under an X-ray?
Oh, good question.
That is a good question. And the answer is it depends. It depends. It depends on the kind of X-ray you're using. Oh. So if you use what's called a high energy X-ray, X-rays are like light. It has a wavelength.
Yes.
If the wavelength of the X-ray is really high, then it has about the same wavelength as the separation of atoms in that material. Wow. So you can shoot the X-ray into that material and it will kind of reflect off at specific angles. Oh. And by measuring that really, really carefully, you can then work out where the atoms are in that material. That's called a scattering.
Oh my gosh.
Yeah.
Wow.
It's pretty amazing.
That's unbelievable.
Yeah, it is.
Yeah,
it is.
That's one of the really cool things about X-rays is you can get down to atomic resolution of where stuff is in materials. Another cool thing. I'm
sorry.
No, go ahead.
I'm imagining like in a Guardian of the Galaxy movie or something where they do that CGI and they go all the way down into that atomic. You're actually seeing where specific atoms are.
Oh, yeah.
In a piece of something. That's incredible.
It is. Yeah. It's really amazing.
I never get tired of that. There are also ways you can do what's called microscopy and get down to looking at magnetic structures using X-rays. And you can get down to a size scale of about, let's say, I think the best ones can go down to about 5 nanometers.
Oh my goodness.
Yeah,
Whoa.
so like a human eyelash is a 1/10 of a millimeter.
Right.
And a nanometer is like 100,000 times smaller than that.
Oh my gosh.
So really, really, really tiny scale. So you can look at the atoms, and then you can also look at how those spins that I was talking about actually get arranged down to the level of 5 nanometers.
That's incredible.
I totally understand why you're so excited about the stuff you're doing.
Right? Yeah.
Totally get it.
It's fun.
It's amazing. And it's not science fiction. Like, this is real.
Yes.
This is what you get to do. Oh my gosh, this is amazing. Well, we could talk to you forever, Dr. Dario, but we are at that time where we ask our guests to give our listeners a challenge. I'm very curious to hear what your challenge will be for our listeners.
Okay, I've got 2 challenges for the listeners of Solve It for Kids. One is to get a magnet, and in particular, if you can get one of those really strong magnets that you see sometimes. They're often like colored silver. So you should check with your parents first because they have to know about the magnets because the magnets can stick pretty strongly to things. But check with your parents first, and then see what you can pick up with that magnet. So try it on something like a pencil. See if that'll work. Try it on a plastic spoon. Try it on a metal spoon. Try it on a paper clip. If you happen to have hair, which I don't, but that's okay, you can try it on a hair clip. And if you use a hair clip, you can try different parts of the hair clip. Like does the plastic part stick? Does the metal part stick? And see if you can figure out what things stick to magnets and what doesn't.
Okay.
Another cool thing you can do with a magnet is you can make your own compass.
Ooh, I like that. Yeah.
So you can take one of these strong magnets, these little silver magnets, and grab something like a needle again, check with your parents first.
Yeah.
Because needles are sharp. And then you can rub that magnet in the same direction, maybe 25, 30 times on that needle.
Okay.
Okay.
And then take the magnet away. Put that needle on something that floats in the water, like a little piece of cork. And then put that needle on the cork in a bowl of water.
Okay.
And what you'll see is that needle should align with that magnetic field of the earth that we were talking about before.
Wow. So you just make your own little compass. I like that.
You can make your own compass. Yeah.
That's
Super.
so cool. Jeff, you'll have to try that with your daughter.
Totally.
Fun. And let us
Totally.
know.
I think I need a stronger one because my fridge magnets aren't quite that strong. But but we're definitely, if we don't have one, we're definitely going to get one because I think that's fun because I know exactly where north is from my house.
Yeah.
So I'll be measuring. I'll be checking to see. And
That's
I love that you
fantastic.
brought in 2 challenges that bring all of our listeners, kids and adults, right into your world.
Exactly. Yeah.
Yeah.
Exactly.
I hope they do come into my world. We need more and more people doing these sorts of things.
Oh, yeah. This would be fabulous. Well, I know you have 2 of us here. Jeff and I will just show up one day and help you.
Come by anytime.
Well, this has been such a wonderful chat. Thank you so much for being on Solve It for Kids, Dr. Dario.
Thank you, Dr. Dario.
Oh, thanks for having me, Jen and Jeff. This has been a lot of fun.
Whoa, the answer was a little more frightening than I was expecting, but I am really glad that we had this chat with Dr. Dario.
Oh, absolutely.
And his challenges, he gave us 2 of them, remember everybody. Using your regular fridge magnets, go around the house and find out what you can pick up. I know some of us have done this before. It is time to go do it again because you never know what things in your house are going to have those attractive metals and which ones aren't and be magnetic.
Exactly.
And then I know lots of us have heard about this second challenge, but I bet we haven't done it. Listeners, it's time to do it. Let's make our own compass.
Yeah. Oh, I've done it. It's been a really long time. I think I did this in grade school, which we won't talk about how long ago that was. But everybody should try it. It's so fun. And, I also, one thing that I've tried too is sometimes when I'm looking at my fridge magnets, I compare their magnetic qualities, right? Like some of them are stronger than the other. I mean, you can get into all these different things, right?
Oh, definitely. I think all of our listeners are going to grab the strongest magnet they have on their fridge to use for this first challenge.
Absolutely. And if you do that, of course, share your stuff with us. We would love to hear what your experiments have resulted in. Remember, we are at KidSolve at Facebook, Instagram, and Twitter. And don't forget to check out our website, solveitforkids.com, where you will find information about Dr. Dario, about magnets, and we're going to give some book recommendations so you can learn more and experiment more. Maybe you will become a professor of physics one day and study magnetism yourself.
Maybe, and it might start with this challenge. When you're doing this challenge, we want to know if you find something magnetic in your house that you didn't expect, something surprising.
Exactly.
So please share that with us. Until next time, you'll hear Jen and Jeff on Solve It for Kids.